Hello. I will here give you the first lecture of a course about adiabatic radiofrequency potentials that provide us with interesting features for confining and studying quantum gases. So this lecture is done in the frame of the course of Vanderlei Bagnato at USP. So quantum gases are really great systems that provide us with a very high degree of control of their external and internal degrees of freedom. And for this reason, they are ideal both for precision measurements used in atom interferometry and for quantum simulation, as proposed by Richard Feynman in the early 80s. The Bose-Einstein condensates and Fermi gases allow you to control the temperature of the gas in the range of nanokelvins, and also the interaction strength between particles, as shown here in this picture of chromium atoms, which expand really anisotropically because of their dipolar interactions. On the other hand, what is really nice with these systems is that you can confine them in really diverse geometries. This includes optical potentials, optical lattices that give you periodic potentials mimicking the periodic lattice for electrons in solids, or confinement to low-dimensional systems, one-dimensional, two-dimensional, or rings, as in this picture. And they also provide several internal states if you want to make mixtures between different species, and also different statistics, both bosonic or fermionic. And finally, you can really nicely image them in absorption imaging as or fluorescence, as is this picture. And this easy detection make this system really ideal for a study of quantum simulation or interferometry. So in this course, I will show you how to access various confinement geometries for quantum gases using a combination of static and radiofrequency magnetic fields, known as RF-dressed adiabatic potentials. This will allow us to provide, for example, double wells, where you have a tunneling between the two wells, or two-dimensional quantum gases, ring traps, bubble traps. We will see how to realize all these potentials, especially in the second lecture. So the first lecture will be dedicated to the basics of dressing atoms with radiofrequency fields, and the second lecture on examples of what we can do with adiabatic potentials. The outline of the first lecture is as follows. I will start to go back to what are spin states and how they interact with magnetic fields, up to the point where I will show magnetic traps. And then I will introduce radiofrequency and see what happens to these Zeeman or magnetic states when coupled to an RF field. So before I start with spins, let me set a little bit the frame of these adiabatic potentials, which rely on the adiabatic theorem, which states that even if some parameter is changing, an atomic state can follow everywhere an eigenstate. So the idea is the following. You write the Schrödinger equation for the state psi with a Hamiltonian that depends on an external parameter lambda. So in our case, this external parameter will be either the magnetic field or the radiofrequency field, or both. So for any given lambda, of course, you can diagonalize the Hamiltonian and find the eigenstates, the eigenenergies, and the splitting between different eigenenergies. So all that also depends on the parameter lambda. So now, the question is, what's happening when this parameter varies with position or time? The adiabatic theorem states that if lambda varies slowly enough, then the atomic state will follow adiabatically the local eigenstate psi of lambda everywhere. So the condition for this to happen is that the variation of the state, because of the variation of lambda, must be smaller, not as fast as the splitting between the adiabatic states themselves. So in this example, as a function of lambda, the second state varies that way, the ground state like that, and the second excited state like this. And so each time that, for example, if we start in the second state, lambda varies, that variations of lambda must ensure that the state varies not as fast as this splitting between the different adiabatic states. So of course it is more critical when the two states are close to each other in this picture at that point, or at that point where transitions into other adiabatic states may occur. So these transitions are called Landau-Zener transitions. And of course, for it to be valid, the adiabatic theorem, two different levels should not touch themselves, because if they touch, then delta is 0 and you cannot ensure adiabaticity. So the states that I will describe in this lecture and the following lecture are assumed to follow the adiabatic theorem. So now let's concentrate on spins and how they behave in magnetic field. So this picture represents the Stern-Galler experiment, where when you send neutrons in a gradient of magnetic field, two different neutron states are split because of the effect of the magnetic field on the spin that acts as a shift of the energy or as a force. So before we apply a magnetic field, let's recall a little bit the internal structure of atoms. I will take the example of alkali because that's very simple atom with just one electron in the outer shell. The electron states are denoted with their principal quantum numbers, which for the ground state of rubidium is 5. And then there is the spin, the electronic spin, and then the angular momentum and the total angular momentum of the electron. So for our rubidium atom, which has a single electron in the outer shell, the electronic spin is one of one electron, so this is 1/2. So we note that 5, 2. So now let's look at the angular momentum of the electron. Well, it depends if we're in the ground state or in the excited state. In the ground state, the angular momentum is 0, we note it S, and it is 1 in the excited state that we note P with the spectroscopic notation. And now, because we have both the electronic spin and the orbital angular momentum, there is a spin-orbit interaction where you will have to add these two spins to get the total angular momentum. So this gives rise to new states, substates, which are called the fine structure, and where the total angular momentum can go between L minus S and L plus S. So of course in the ground state where L is 0, there is only one choice for J, it is 1/2 as the value of S, and the ground state is 5, 2, S, 1/2. In the excited state where L is equal to 1, there are two possible choices for J, either 1/2, and this is a state 5, 2P 1/2, and 3/2 for the other excited state 5, 2P 3/2. Well, now in atoms there are also sometimes a nuclear spin. So this is the case, for example, in rubidium 87, where the nuclear spin is 3/2, and we have to add the nuclear spin to the total electronic angular momentum to get the total angular momentum of the atom. So as I is 3/2 and in the ground state J is 1/2, we come with two different total angular momentum states, so denoted as F, either 1 or 2. And the splitting between these two ground states is called the hyperfine splitting. In the excited state for P 1/2, there are also two states, and in the second excited state, as P is equal to 3/2, there are 4 different excited states. So for these lectures, we will concentrate on atoms in their ground state. And so in particular, when I have rubidium in mind, I will concentrate on the lower ground state, F equals to 1, which has 2F plus 1 degenerate systems, substates, where the quantum number for these substates varies between minus F and plus F. So let's look more closely at the eigenstates of this ground state, F equals to 1. So we consider the atomic ground state with a total angular momentum F, and we wonder what are the eigenstates of this total angular momentum operator. So if we fix some axis Z, we can show, because F squared and the projection of F on the axis Z commute, that they can be diagonalized in the same basis that is noted M with an index Z, just to see that we have projected F on the axis Z. The eigenvalues are F plus 1 h bar squared for F squared and M h bar for M. So only some values of the projection of F on the Z-axis are allowed. Only the values minus F plus 1, etc., up to F. And the whole basis can be built starting from minus F, for example, by applying the raising operator F plus, which, starting from some state M, transforms into the state M plus 1 with some coefficient. So you start from there, you apply F plus, and from that point you can construct the whole basis. So it could be also the other way around. With F minus, you start from here and apply F minus to F times up to minus F. So the F plus and F minus operators are obtained from a combination of the projection of the angular momentum onto the X and Y axis with plus and minus I. So of course, if I write F plus minus Y minus like that, it means that Fx is the sum of F plus and F minus divided by 2. The second important remark is that the operators which ensure the spin rotations about some axes U and with an angle theta are written as an exponential of the projection of the total angular momentum on the axis we want to rotate about. So this formula will be very useful for us to manipulate spins. So as spins are vectors with a given length, to go from one state to another state, what we do in general are spin rotations using this operator. Okay, so now let us introduce a magnetic field. What will happen to our spin? The Zeeman effect will shift the different M states, which were initially degenerate, proportional to the amplitude of the magnetic field. So the interaction between our spin and the magnetic field writes as a scalar product, just as it is the case for classical physics, where the energy of a magnetic moment is equal to minus B minus mu, the magnetic moment, times the magnetic field. So here our magnetic moment is given by this expression, so proportional to the Bohr magneton, which is the magnetic moment just for one electron, the Landé factor, which gives us the magnetic moment for our atom, and then this is divided by h bar to get the ferromagnetic ratio. So we can write our Hamiltonian as some frequency times the projection of our spin onto the axis of the magnetic field. And so this frequency here, which is proportional to the magnetic field, is called the Larmor frequency. It is the amplitude of the magnetic field in units of frequency. So now if we look at our Hamiltonian and want to write the time evolution, using, as usual, exponential minus I Hamiltonian T over h bar, what we find is that, in fact, this time evolution is just a rotation of a spin, as we have seen just before. Exponential of I, an angle, times the projection of our angular momentum along the axis U of the magnetic field. So what's happening, for example, if I choose the Z direction along the magnetic field, is that the spin precesses around the magnetic field at a frequency which is equal to the Larmor frequency. So the eigenstates of the spin operators are the same as the eigenstates of the projection of an angular momentum. So of course, that's again these M states from minus F to plus F, where I have to take now the direction of the magnetic field and not any arbitrary direction. So it is Z if I choose the Z axis along the magnetic field. So the eigenenergies, now in the presence of a magnetic field, they are not all equal to each other. There is a shift, which is called the Zeeman shift, and the different magnetic states are shifted proportional to the Larmor frequency, or equivalently to the magnetic field. In the case of equals 1, there are 3 eigenstates shifted proportional to the magnetic field. So now, how can we, with that, produce magnetic traps? I have discussed the case of a homogeneous magnetic field before, but if the magnetic field depends on position, then at each point of space I have to apply the reasoning I had before. And I am exactly in the situation of adiabatic theorem I introduced before. So at each point of space I have a spin operator that I have to diagonalize. I know the eigenstates, but now the question is, will the atom follow the eigenstate everywhere if I go to another position? And this will be true if the motion is slow enough with respect to the splitting between the eigenstates. So if this is the case, we end up with 3 different potentials for the 3 different spin states of f equals 1, v1, v0, v minus 1, which are split locally by the Zeeman splitting corresponding to the magnetic field. So in this potential, for example, we speak of low field seeker because the atoms will be attracted to the regions where the magnetic field is less. Here it's high field seeker because the atoms will be attracted towards the regions where the magnetic field is larger. So in general, we can build traps using the low field seeker state because we can produce minimum of magnetic fields but not maximum of magnetic fields. So now let me give you a few examples of magnetic traps, starting with the simplest one. We take just 2 coils with opposite currents. This creates a spherical quadrupole with a field which is 0 in the center and then increases when you go away. So this is the expression of the magnetic field. So if I take the magnetic field along the x-axis, for example, I see that it increases linearly with x, so giving rise to a magnetic trap where the state m equals 1 is trapped like that, m equals 0 is unaffected, and m equals minus 1 is anti-trapped. However, you see here that here I have a problem because I told you for adiabatic potential to apply, the states should not touch each other. So here the minimum of the magnetic field is 0 in the center, so the adiabaticity condition cannot be fulfilled. And in general, when people use quadrupole traps, either they deal with hot atoms or they have a trick to prevent the atoms to visit the central region where the magnetic field is 0. There is another way to get rid of this problem. This is to use a field configuration where the minimum is not 0. So this is the case for Ioffe-Puchard trap, where you have 4 bars with alternate direction of the currents, which create a 2-dimensional quadrupole in the x, y, well, here in the yz plane, sorry, and 2 more coils along the x-axis with the same direction of the current, which produce a curvature of the magnetic field able to trap the atoms along the x direction. So in the xz plane, the field has this shape, and in the center where the amplitude of the field is minimum, there is a non-zero magnetic field with a direction along x. So if we look at the corresponding potential, we can make an expansion and we find that it is harmonic with a cigar shape with a frequency, a trap frequency which is much larger in the radial direction than in the longitudinal direction. So this one has a non-zero minimum near the center. Okay, so we have seen how to confine atoms with magnetic fields. Now let us introduce one more ingredient, and this is a radiofrequency field able to couple the different magnetic substates at some position resonantly. So a radiofrequency magnetic field is just another magnetic field that we can write as some amplitude which is modulated in time at some frequency omega. So for convenience, I will take the static magnetic field for the moment homogeneous along the z direction, and the oscillating field, I will take it along the x direction, and this is linearly polarized. I come with the Hamiltonian as before, minus gamma times the angular momentum times the total field. So I have, as before, the field for the Zeeman splitting with the Larmor frequency omega 0 corresponding to the static magnetic field. But in addition, I have the oscillating term with some amplitude, which is called the Rabi frequency of the RF field, equal to GF mu b b1 divided by h bar, times the direction fx of the spin, and with some oscillation with time. So what is the effect of this new term to our usual Hamiltonian of the magnetic field? So we can write this cosine omega t as a sum of exponential minus I omega t and exponential I omega t. And the fx term, remember, we can write it as f plus f minus, so a combination of the raising and lowering operator. So as we have this raising and lowering operator, we can see that we will able now to change the m state, the eigenstate of fz, because this changes m by +1 and this by -1. So now if I make the multiplication between these two terms that appear here, I can write the Hamiltonian into this form, so my former static term, and then I have grouped together the terms in exponential minus I omega t with f plus and exponential plus I omega t with f minus, and this is the other term with minus I omega t with f minus and the Hermitian conjugate. Here I have introduced omega plus divided by 2, which is the weight of the polarization of the RF field onto the sigma plus polarization. So the sigma plus polarization is just, by definition, the weight which is in front of f plus. So in this case of linear RF field, omega plus and omega minus, the weights on sigma plus and sigma minus polarization are just equal. You can decompose linear as sigma plus sigma minus. But in the general case, if I take another polarization, arbitrary one, what I have to define as omega plus is the weight of my complex radiofrequency field on the vector defining the sigma plus polarization. And we will see that this is this term which is very important. So now to solve our problem, let me consider two different coupling regimes. To start with, if the coupling omega 1 is small, we have the weak RF coupling regimes, and what's happening is that our RF will couple the Zeeman state in the +1 state to the Zeeman state 0 at some position where the splitting, Zeeman splitting between the two states corresponds to h bar omega, the energy of one RF photon. So transitions will be induced, and then the atoms, if they were trapped, they will be lost. And this is one way, for example, to cool the atoms, which would be trapped here. If they reach this point, they are lost, and that's how we cool the atoms by evaporation. However, if the RF coupling is strong, then it is strong enough that we have to consider new eigenstates, which mix the upper state with the lower state here. It is so strong that if I start in this level and I arrive at that point, I will, with 100% efficiency, reach that point and follow this potential, and then reach that point again and follow this potential. So it means that we have to consider new potentials that are a mixture between the potentials of my different Zeeman states. And these new states that mix the different magnetic states are called the Dray state. And this will be valid if the adiabatic theorem applies, so that's why we need that the splitting is large enough, and so that the coupling is large enough. So let us go into really the problem and solve our Hamiltonian. The point is that now we have a Hamiltonian that depends on time because of the e to the I omega t term. And so to solve this problem, we would like to get rid of the oscillating term and go back to a time-independent Hamiltonian. So for that, we will look for solutions, psi tilde, in the frame which rotates at frequency omega around the z-axis. So let me introduce the rotation operator biangle omega t about the z-axis, the operator u. U dagger now writes exponential I omega t fz divided by h bar. And my state psi tilde will be equal to u dagger psi, or equivalently, the initial state psi is equal to u psi tilde. The effect of u onto the fx, ny, fz, f plus, f minus operators is as follows. So I will concentrate on the effect on fz and f plus minus. Of course, because in u there is just fz, it will commute with fz, and the effect of fz is just nothing. However, the effect of u on f plus and minus is to introduce a phase shift, which is equal to exponential I omega t for f plus and minus I omega t for f minus. So now the question we have is, for our new state psi tilde that we have introduced, what is the Hamiltonian that it obeys? So if we have an Hamiltonian h prime for psi tilde, it must obey that h prime psi tilde is equal to I h bar time derivative of psi tilde. Psi tilde is equal to u dagger psi. So if I want to compute the time derivative of psi tilde, I should derive this quantity. So I will get two terms, the one which derives u dagger, this term, and then the one where the derivation applies on psi. This is this term. Now, the time derivative of u dagger, if I look at this, it is just I omega fz divided by h bar. So if I multiply I omega fz divided by h bar by I h bar, I get minus omega fz. So the time derivative is this one, minus omega fz, u dagger psi. And now the other one, I h bar time derivative of psi is by definition the Hamiltonian applied on psi. So we have here u dagger, initial Hamiltonian applied on psi. Now if I remember that u dagger psi is just psi tilde, I introduce psi tilde here, and that psi is equal to u psi tilde, I can write everything as a function of psi tilde, and I get that h prime psi tilde is minus omega fz plus u dagger hu applied on psi tilde. So my new Hamiltonian is the Hamiltonian h transformed by u, so rotated around the z-axis at frequency omega t, minus omega fz with a correction. So we have to compute this new Hamiltonian. Remember that this is the expression for our Hamiltonian h. So what is our h prime? We have the term minus omega fz, which is here, that I just add to omega 0 fz because the application of u dagger u to fz does nothing. And then if I apply u dagger u to f plus, I get exponential plus I omega t, which will just cancel with this time dependence. So this term will be time independent, and of course this is also the case for the Hamiltonian conjugate. Concerning this term, f minus will give exponential minus I omega t f minus. So instead of cancelling the time dependence, it will amplify it, it will be modulated at frequency 2 omega. And the same for the Hamiltonian conjugate. So we get a static term as we wanted, plus a term which is oscillating very fast. And at this point, we will apply the rotating wave approximation, which consists in neglecting this fast oscillatory term. And we just get, finally, the new Hamiltonian for psi tilde, which is minus delta fz, where I have defined the detuning as being the difference between the RF frequency and the Larmor frequency, plus omega plus times fx, where I have added f plus and f minus to recover fx. So this expression is valid as long as the RF coupling and the detuning are very small as compared to the RF frequency itself. This is why we can neglect this term here. We have small coefficient, and here something fast oscillating. So from now on, we will work with this Hamiltonian in the rotating frame. So now if we look at this Hamiltonian, what is it? Finally, it's just, again, the Hamiltonian of a spin. If I define overall amplitude omega, which is just square root of delta squared plus omega plus squared, I can write this expression as big omega times some cosine fz plus some sine fx. So it is just an amplitude omega times the projection of my spin onto a new direction, u theta, given by cosine theta ez plus sine theta ex. And the cosine theta I have to choose for this to be valid is minus delta over big omega, and the sine omega plus over big omega. So now that we have written the Hamiltonian as the one of a spin, we know what are the eigenstates and the eigenvalues, of course. And the effect of the RF spin is just to have rotated all the spins and operator about the direction y by an angle theta to get f theta. And now that we have the Hamiltonian under that form, we are back, like in the case of the usual magnetic field, we have a spin precession around the new axis f theta at angular frequency big omega. So this is our new situation. So the eigenstates, which are the eigenstate of f theta, are called the dress states because the atoms now are dressed by the RF field. And so they write m in the direction theta, and their eigenenergies are just m times h bar omega, or if you prefer, m h bar times square root of delta squared plus omega plus square. So this was the case for a homogeneous magnetic field. Now, if we have position dependence for the magnetic field and for the RF field, then the Larmor frequency will depend on position, and the RF coupling will also depend on position, which means that the energy will depend on position, the states will depend on position, and as soon as we follow the adiabatic theorem that these states vary slowly as compared with the difference of energy between states, which is given by big omega, then we can consider that we have adiabatic potentials for our states given directly by the energy at each point r. So this is the RF dressed adiabatic potentials we wanted to derive in this lecture. So we can also describe what we have just done by a simple drawing, starting from the initial magnetic states. For example, if we confine the atoms in the upper Zeeman state, we introduce an RF in the regime of strong coupling. The RF field will be resonant at some position where the RF frequency is equal to the Larmor frequency, giving a detuning 0. It will provide us with a very efficient spin flip to the other state. And if, in fact, we consider the energy of the lower state plus the energy of a radio frequency photon and the energy of the upper state minus the energy of the radio frequency photon, we see that all these energy become degenerate where the detuning is 0. So these are these potentials shifted by the effect of the RF transition. I come from that potential. Because of 2 photons, I go into that potential, and then again 2 more photons exchange. I end up in that potential. So this could be the new potential we have, but because of the coupling, strong RF coupling, this crossing is not a crossing but an anti-crossing. There is a splitting equal to omega plus at the crossing, and this completely corresponds to the potential I have written before. So the square root of delta squared plus omega plus squared is exactly this line here, and it is minimum when the detuning is 0, and then the splitting is equal to omega plus. So this projection on the sigma plus polarization of the RF will set us the criterion for adiabatic theorem to apply. You need that the splitting omega plus is large enough with respect to the typical variations of the states for adiabatic states to be valid. So let me now summarize a little bit on what we have learned and give you the typical shape of these adiabatic traps in the more general case. So we consider this adiabatic potential, and we will restrict ourselves to low field seekers with a positive value of m. The detuning delta, which is directly given by the Larmor frequency, varies quickly, as fast as the magnetic potential itself. The radio frequency coupling omega plus in general varies slowly, especially if we shine a uniform radio frequency field, and its variation is essentially due to the variation of the relative orientation of the magnetic field and the RF field, because we have to take at each point the projection on the sigma plus polarization. So if B0 changes, it changes the definition of sigma plus polarization. So because this varies slowly and this varies quickly, to a good approximation, the trap minimum will lie where the detuning is 0. So this gives us a surface, an isomagnetic surface, where the potential minimum will lie. So this is a resonant surface. In the direction transverse to this surface, the atoms are strongly confined with approximate harmonic potential, and the harmonic trapping frequency is given by this value, proportional to the transverse magnetic gradient and inversely proportional to the square root of the RF coupling, and this we will see in lecture 2. So inside the isomagnetic surface where the atoms are confined, of course, as delta is 0, the potential is just equal to mh bar omega plus. So if there are variations of omega plus inside the surface, this will give us the locations where the potential minimum will be. But if you are on Earth, where gravity is present, you have to remember that you will have to add this RF adiabatic potential with gravity, and this may also change the equilibrium position of the atoms if gravity is preponderant. So the first experimental realization of the RF dressed traps was done about 18 years ago. And it was done using a Yoffie-Pritchard trap. So this is a picture of the atoms initially in the Yoffie-Pritchard trap. And then 2 pictures where you see that the radio frequency here corresponds to some first value where the atoms have to lie on the isomagnetic surface corresponding to Larmor frequency equals to this first value. So this gives you some isopotential with some radius. And for another value of the RF field, you have a larger isomagnetic surface. And because of gravity, in this example, the atoms are at the bottom of the bubble that is done with the dressing field. So in the next lecture, we will see many different geometries that are accessible with RF potentials. I end with giving you 2 references that may be useful for all the course. So the first reference gives you a detailed theory of RF-based adiabatic potentials with step-by-step derivations of all the theory, and which goes beyond this short course. And the second example gives you a gallery of different traps you can make with RF-dressed adiabatic potentials, and with more focus on the practical examples. Thanks for your attention.